Let V and W be vector spaces over the field F having the same finite dimension. Let T be a linear transformation mapping elements from V to W. Then T is said to be invertible if there exists a linear transformation S from W to V such that S of T of X is equal to X for all vectors X in V. In casual terms, S undoes what T does to every input. Now, under these assumptions, we can actually show that given a linear transformation T, being invertible is equivalent to being bijective. And from the definition of invertibility, it doesn't look like this is a very easy condition to check. But let's look at some examples. First of all, linear transformations corresponding to elementary row operations are invertible. Now let's consider the linear transformation T from R3 to R3 and given by T of xyz equals xy0. We're going to argue that this is not invertible. The way we're going to do this is interpret this geometrically. So T is a linear transformation from R3 to R3, so it maps elements in the R3 space to an element in the R3 space. So let's draw the R3 space here. So I have my xyz axis. So this is the point 111, and if you drop a vertical line down here to the xy plane, this is what we have. And this point on the xy plane is precisely T of 111, because this point here is 110. But if you look at another point, say 112, it also gets mapped to the same point by T because T112 is also 110. And in fact, if you consider the vertical line that goes to this point 110, every point on the vertical line will get mapped to this point 110 by T. So from this, we see that there's no unique point that gets mapped to the point 110. And so if I ask you what would be the inverse of 110, there's no such choice. So there cannot possibly be a linear transformation that is the inverse of T. Now there's a special name for this kind of linear transformation T here. As you see, it basically projects the points in R3 to the xy plane, and we call T a projection. Finally, if you have a linear transformation T given by T of x equals A times x, where A is an n by n matrix with entries from some field F, then T is invertible if and only if the matrix A is invertible. So for example, if we have this linear transformation here, we can check if T is invertible by making the following observation. So we can first rewrite this as 2 minus 1, 1, 1 times x1, x2. So we have now written the linear transformation in this form here. And so we just need to check if this is invertible. And we don't really have to find the inverse of this. We just need to compute the determinant to see if it's 0 or not. And the determinant of this is clearly non-zero because I have 2 times 1 minus 1 times minus 1, and that's going to be 3. This matrix is non-singular, so T is invertible.